All right, we are now recording. So I'm Conan Poppy. I'm the technical workshop manager for the IEEE student chapter here at SDSU, and I'm going to be teaching you the very, very basics of making electricity with copper wires and magnets. This is going to be like pretty informal and also very basic. Like we're not even going to go into multiple phases or brush coils or commutators or anything like that. This is just like the bare minimum knowledge you need to know how to magically create electricity. So let me share my screen real quick because I have a little PowerPoint. Can you all see that?
Yep.
Okay, you can see me going through it right now, right?
Yeah.
Okay. So I'm going to show you how to make a very simple generator. Now, this on the left is at Hoover Dam. So these are very not simple generators. These are huge hydroelectric power generators. You can see in this center picture, all of these kind of brownish bars, these are all gigantic copper coils. But what we're going to be doing is a lot closer to this picture on the right, where it's just one little coil. You could put this on like a cardboard box and put a nail through it and spin around a little magnet and make a little light bulb light up. So that's going to be the extent of our efforts here today. Oh, by the way, if any of you have anything like questions or anything at all, just go ahead and yell. Like, this is super informal. This is not a lecture. Just imagine like we were at the school. This would just be us hanging out in a room right now. Okay? All right. So the basics that you need to make electricity, you just need a copper coil and some magnets. Or even, you really just need one magnet. You need a north pole and a south pole. And the reason that we use copper is because it's just really conductive. You technically could use any metal as long as you could get electrons to flow through it. But copper is super conductive. There's like no resistance in it. That's why we use it for all of our electronics. It's easy to push electrons through copper. It doesn't take much effort at all. So the magnets are how you do that. As you pass a pole near these electrons, they're going to try to move out of the way. Or if it's the south pole, they'll be trying to move towards it. So as you rotate this through your coil, it's going to be pushing and pulling the electrons within your copper around. Now, if your coil is open, so you have an open circuit instead of a closed one, there's nowhere for those electrons to go. So you're not going to have any current. But as soon as you close it, you would actually notice, and some of you may even be able to test this if you have a magnet that's not already on that rotor in your kit. Because if you take a magnet and start just passing it over your coil, you might actually feel a little bit of resistance because your body is actually completing that circuit. Now, it's not going to shock you because this is nowhere near strong enough to create that kind of charge, but you just might feel a little bit of resistance in your magnet. And that's because you're actually pushing and pulling electrons as you move it, which I think is kind of cool, but it's hardly noticeable with our setup. You only have about 200 turns of copper in your little bundle right there. And to really notice anything, you'd probably need about 2,000 turns, which is what real generators have inside of them. Which brings us to what's happening inside of a basic generator. So this is kind of what I was talking about. As you're moving your magnet past it, you're causing electrons to flow. When you connect this circuit, there's actually somewhere for the electrons to go to, so they start to create current. And just a really, really quick, how far into your EE or Comp E classes are you guys?
I mean, I'm up in the 400 level.
Okay, so you're probably pretty familiar with magnetic coils and how all of that works.
Yeah, I've been hearing about it for a while now.
Yeah. Is everybody else kind of like at the 380 level or at least 310?
We're going, over this in 310 right now, actually.
Okay, cool. So you've got the basics already. So I'm probably just like preaching to the choir here. But but it's nice to visualize it, because I remember when I took 310, I never saw anything quite like this. It was just sort of like hand waved, like, oh yeah, it creates a current, moving on. But this is actually how it creates that current, and why you use copper instead of anything else. It's because it's so easy to make that current. Like you can see with our little setup here, you really don't need that much copper, and you really don't need that big of a magnet to make something happen. Now, it won't be very much, but it is something. So, the part you've all been waiting for, let's actually build this thing. So this is what your guys' kits look like, right? Like you've all got 3 little bearings, your little rotor guy there should have 2 gears, a big one, a little Christmas light. Does this look like what you guys have?
Yep.
Yeah.
All right, cool. So this is going to be the first thing that you do. And this is also, in my opinion, the trickiest part. So you should all have your little coil. Hang on, I'm going to get up and grab mine real quick. All right. So if you've all got your coils, oh, and if any of you are having problems, just let me know and I can let you all share your screen and we can try to troubleshoot together. So you'll want to, the way I do it is I take that coil and on the opposite sides of the electrical tape, I just like stick my finger through, because you're just trying to like spread it out a little bit so that you can stick the rotor inside of it. And it might be kind of tight to fit over your stator. So the stator is that barrel that you're pushing your rotor through. The rotor is that shaft. Is that making sense? Are you guys getting it over there? It doesn't have to be even when you spread it out or anything. You just have to separate so that you have kind of like 2 loops that are being held together by the electrical tape.
Yours looks cooler than mine.
Oh, that's because Jason. So Jason is with 3D4E, and he's the one who he actually printed all of these components for us on a 3D printer that he built himself at home. Oh, I think I have chat. Okay, that's cool, Ben. So he printed them himself. He actually ran out of the white stuff, the white filament. So I got 1 little stator that's in blue. Would it have been cooler if we all got blue ones?
Yeah, I was just commenting.
Yeah. Because I think we're going to end up making more, because I still have more people who want them. And we just kind of, yeah, I got a couple emails this morning saying that people wanted more kits, and we ran out. So we'll have to make some more.
I think in general, it's a pretty cool project because it's like hands-on, and I feel like with the Corona and stuff like that, people don't, get to do as much stuff anymore. So it's like, this is really cool.
Yeah, I really wanted to have the first workshop be something that you could actually put your hands on. I think the workshops after this are all going to be sort of like programming or computer programs, things like that. But I wanted to at least give you guys one that you could put on your desk,
Yeah.
So does everybody kind of have theirs separated like that?
Still working on it. But.
Okay. Yeah, I know they're a little bit tight because you can see in this picture, I don't have nearly as much copper as I gave you guys. So I think when I put this one together, I only did about 100 turns and I was getting almost no voltage out. So I doubled the turns for you guys. So it's going to be a little bit harder to fit. Out of curiosity, which screen is being shared for you guys right now? Is it the one that shows 2 slides or just 1 slide?
2.
I wanted to show just the 1. Well, you guys can see the next step. You're looking into the future.
You guys probably can continue on if you guys are done with this part, because
Yeah, I mean, since I'm recording this, if you miss something and you want to go back and relook at it, you'll be able to find this. We're going to set up a YouTube channel for all of our IEEE stuff, so you'll be able to look it up there. Or I can just send you this PowerPoint through an email or something. But we'll go on to the next slide. So now is the part where you're actually going to use one of these bearings, and you'll see that once you put your little rotor through that coil and inside the stator, you'll want to take a bearing and put it on that one peg that's all by itself. It should just slot right in there pretty easy. It's not going to fit super tight or anything, but that's okay because it just needs to stay in that little hole. And then the stator, so in mine it's blue, for you guys it's going to be white. You'll just take that whole assembly with the rotor inside of it and kind of put it down into those two slots on the bottom of your white board. And you'll kind of have to finagle your rotor into that bearing. So the thinner peg on your rotor that's got like that's got a little cut in it, that's going to go into the bearing. You'll be able to push the whole thing down so it snaps into those two little slots in your board. It doesn't have to fit like perfectly flush or anything. They're just there to hold it a little more stable. So you can push it down until you hear it click, or just until it stops moving. You shouldn't have to force anything. If it's tight, that's good enough. Okay. I think we can go on to the next step. Does anybody have any serious objections to that? All right. So now, looking at the other side, you can take another bearing and just put it down into that slot. There won't be anything inside that bearing yet. Once it's in that slot, that's when you put the smaller gear through it. And you don't have to force this smaller gear very far. It only has to go down, I mean, that's probably, what does that look like? 1/4 of an inch, 1/3 of an inch. That's all the further that you have to push that in. Just enough that the shaft on the smaller gear is inside that square hole for the rotor. And then next, you'll take your third and final bearing and put that inside of the big gear that says IEEE SDSU on it. Again, it should fit snug. It's not going to be too tight, but you also don't want it to be too tight. So if anything feels like you have to force it on, you're probably trying to push it too far. All right, and then you can just slot that big gear onto your last empty peg. So you should have a peg sitting there with nothing on it, and that's where your big gear goes. And it should fit pretty well with your smaller gear. And then that's actually our little hand crank generator done. That's all it takes. So, in case you're curious or you can't quite tell exactly what's going on right now, all this is doing is turning the kinetic energy of spinning these gears into electricity. And the way that works is you're turning two magnets that have the same poles, so north is one side and south is the other, and you're turning those poles past a coil of copper. Now, if you were to turn it right now, you're not going to feel any resistance on the magnets or anything because our copper is an open circuit. There's nowhere for the electrons to go. So you're not actually pushing or pulling them, they're going to be staying static. But if you were to hook this up to a little multimeter or the light bulb, that's when you would start to feel a difference as you spin it. Now, you'd probably feel that difference better if you tried to spin it with your fingers, which you can do by just popping the smaller gear off, and then you could just grab the bearing on the other side. So on the left-hand side in this picture, you can grab that bearing and spin it yourself if you want to. And you should be able to feel just a slight difference versus when the circuit is complete and when the circuit is open. It's not going to be much because you only have like 250 turns to work with, something like that. I think some of you might have 300. To be honest, I was losing count making all of these turns. But you all have over 200 but less than 300. And really, to make a good voltage, you probably want at least 1,000 turns. So does anybody in here have a multimeter right now?
I do. But I have a question.
Yeah, for sure.
Can you go back to the slide on installing the final gear, the big one? Because I missed that, and I'm not sure if it's going on correctly.
Okay. So is this the one you
okay.
needed to see or the next one?
That one. Yeah, I have support material that's in the, I guess, printed in the gear. So I'll have to pull that out really quick. It's like, there's no spot for the, there's like a honeycomb where the bearing is supposed to sit in. So I got to pull that out real quick.
Oh, dang. Sorry,
Perfect.
I thought I did a good job of cleaning all those out. Did it come out easy or hard?
I'm just about to pull it out. We'll see.
Okay, cool.
It'll probably take a minute.
Okay. Is anybody else having issues? So if you guys do want to hook a multimeter up to this, I'm just going to go back to show you how to do that. So all of your copper coils, I already cleaned the ends of them for you because I wasn't sure if you guys would actually have like a little X-Acto knife or anything. So the tips of your coils are already cleaned off. So all you have to do is either wrap it around the copper on your little light bulb, or you could wrap it around the probes for a multimeter. And then as you turn your gears, you would see on your multimeter that your voltage is actually jumping between a bunch of different values, and that's because we're technically creating an AC current. Because current is only being transferred when one of the poles is passing the coil. So every time it passes, you get a current. But then when it's not passing, you have no current. And then when the other pole passes, you get a negative. You're actually drawing current backwards. So none of those currents are enough to make a huge difference right now. But if this were much bigger and we had much more copper and much stronger magnets, you would be creating pretty hefty AC current. But I think with our 250 turns or so that you guys have, if you actually check it on a multimeter, you'll be getting about 0.25 volts at the peak, which unfortunately isn't really enough to light these little Christmas lights up. So these Christmas lights, when I check them at home, they really need about 1 volt to actually see the light on them. If you put this generator in a really like pitch black room and cranked it as fast as you can, you might see a very faint light on those light bulbs. So the best way to see if you're actually creating any electricity here would be to either feel it on the magnet by that little bit of resistance that you can sort of detect with your fingers, or to actually hook it up to a multimeter.
Yeah, I got it hooked up to the multimeter and working, and it was right about what you said.
Well, that's good. That means I'm not crazy. Okay.
Yeah, it was, and on the AC setting, it was like at max about like 0.1 volts.
Right. So that's a little lower than what I was able to get out of it, but still, yeah, it'd have to be pretty dark to really see it on this light bulb, which is unfortunate. I just couldn't find any lower voltage light bulbs to cut apart and give to you guys. I mean, I know that if you want to, you can just hop on Amazon and find like really low voltage LEDs to hook up to this, and you'd be able to light those up for sure, because I know I found LEDs that'll light on 0.1 volts. Ben, did you notice that if you spin the shaft the other way, you can get negative voltage out of it? You can actually start drawing your current backward.
Let me try that real quick. Let's see. Yeah, it does. It still kind of jumps all over the place, but it does go negative.
Yeah, it's still going to be a pretty hectic AC current. How's everybody else doing? Have you guys gotten it? Yeah, what's up?
Like LEDs that like are, you know, like the LEDs that come from like an Arduino or whatever.
Mm-hmm. Yeah, those are the super little ones that I'm talking about. Like you can light those with almost no voltage.
I don't know where. Maybe I can find it. Just a second.
Yeah. Like I considered getting a bunch of like really tiny surface mount LEDs, but then I would be like asking you guys to solder stuff, and that just seemed a bit too intense for what this generator really is. And I know not everybody has solder kits at home.
Is the issue with the LEDs also that they would only be in like, because they're a diode, they'd only allow current through one direction versus the incandescent bulb in this?
Right, that is one issue. Yeah.
So we have to use like a full bridge rectifier or something to.
Yeah, I mean,
get the whole power out of it.
If you got a small enough LED, you would basically just see it flash, kind of. And not even really flash. It would like dimly light and then just go right back out. So let's talk about ways that we could improve our little generator here. So the two main things that make generators more powerful is more windings and stronger magnets. So in most generators in real life, they don't use permanent magnets like this thing does. Permanent magnets aren't that strong. They're fragile. Like actually, while putting these kits together, I think I broke 6 magnets. So you don't use them in industrial settings. Like those giant generators at the Hoover Dam, those don't have permanent magnets in them. You use electromagnets. So you just start passing electricity through other metals to make very powerful magnets. And then you pass those magnets over like tens of thousands of windings of copper. I just get another chat. Let's look at that. All right, cool. So another way to make generators way more efficient is to use multiple phases. So it would be pretty annoying if you had to run your entire life on a current that was constantly changing from positive to negative, so all the lights in your house were just dimming and then getting bright, and then dimming and then getting bright. Like that would just not be a great way to live. So what you do to get rid of that is you have multiple phases throughout your generator, so that as one pole is passing, you're about to pass another pole. So one way to kind of think about it, and I know it's hard to just hear somebody say it. It's way easier when you can actually visualize it. So the way I think about it is you push for, say, half a second, and then you have to release, right? Well, what if you had a friend who could start pushing another half a second halfway through your push, and then add another friend who's pushing even when he starts? So now all three of you are pushing at slightly different times. You could, whatever you're trying to push, wouldn't even notice that one of you stopped pushing, because the other two are there to pick up the slack when the first one stops. And by the time the last guy is done pushing, the first guy has already started again. So it's kind of the same for the current. Now there's obviously a lot more to it, because like Ben was saying, you have to go through voltage rectifiers, you have to go through inverters to make sure that you actually don't bottom out and go negative. So there's a lot more to it than just, oh, I'll just keep pushing and then it will be fine. But the gist of it is you add more phases so that as one phase ends, another one is already beginning. So to the load of your generator, it looks like the push never stopped. It just kept going and going and going. Now, if you look at this picture right here, it says commutator, and that's because while I said they don't use permanent magnets to really create the voltage, there is at least one very small permanent magnet in most generators and motors, and that's because you need something to start your spin. So you use that one little magnet to start spinning the rotor, and that will charge up your electromagnets, which will actually create your electricity. Now, this is the part where I try to sell you guys to join my team for my big project. And my big project is I want to make a real generator, not this little guy. I want to hook something up to a bicycle so that we can power something big. And that one's actually going to be 3 phases. That one's actually going to need some inverters and some rectifiers and some bridges. Like, that one's going to be pretty intense, and we're going to be working on it for the rest of this semester and all of next semester. And that's not going to be a technical workshop or anything like that. That's just going to be probably me and maybe 4 students who are really into power and who really want to make something go. Because like, that's what I've decided to specialize in. I'm specializing in power systems and things like that. Like, that's what I like. To me, generating electricity is magic. You're passing metal past other metal, and you're making things get brighter. Like, to me, that's magical. I love it. Like, I want to make big versions of it. So hopefully somebody else can be a little inspired by this project and join me on that big one. But we're going to be doing something pretty intense with it. So yeah, if you are interested in that, I'm going to send out another invite to join that team, or you can just email me at either of those down there. Or I think everybody here has my phone number, so you could just contact me that way. But I hope that sounds exciting to somebody. It sounds exciting to me. And then I gotta plug our radio. We have a guest lecturer coming in to talk about the history of radio on the 15th at 3 p.m., and that's going to be through Zoom as well. And if you don't want to copy any of this down, I can send this slideshow to you, and this little flyer is on the Discord as well. So now we are in the troubleshooting phase. Is anybody having trouble with their generators? No.
I mean, I guess I would be, because like I just got here, but I'm just kind of waiting around, like watching everything.
Oh yeah, for sure.
I mean, like I mean, by having trouble it's just not doing anything yet, because I was in a meeting with Arnold, so.
Gotcha. You want me to back up so you can see how to put it together?
Oh yeah, sure.
Yeah.
Okay, cool.
Yeah. So I'm gonna stop the recording right now though. But I mean, I'm gonna stick around. Like, you guys don't have to leave just because I stopped recording.
For sure. All right, so I put one of these in there. I know, but I am interested in that generator project.